All right, good morning. Hope you all are doing well. So now we'll start to look at chapter 13 on interfacing C++ with our x86 assembly language. And we'll look at a couple of examples. And one of the examples in particular will be very similar to the overall structure of your new assignment this week. Um, but one thing that we can do in the Visual Studio environment is we can embed assembly directly within our C++ program, meaning that we can create blocks within the C++ program that are going to do assembly. So the idea being that the overall program is still in a high level language, right? In this case, C++, but we might have certain portions that are going to be in assembly. And we can go back and forth also between the different portions, right? You know, execute some C++ code, go to assembly block, return to the C++ level, go to another assembly block, and and so on and so forth. So we can always go back and forth. And so the idea then in this case is that, you know, the overall program, meaning a lot of the logic could still in this case be in C++, but we might choose to have, you know, certain specific things in assembly, for example, to try and optimize the code. So the second example that we'll look at is going to have things like the output and all that user input, user and output to the screen is going to be done at the C++ level. Um, Although we'll see a little bit next week that you certainly can think about doing that directly at the assembly level, but we'll be doing that at the C++ level, and then there'll be a specific function, a search type function that's going to be done in assembly, but the rest of the program is still done in C++. And the idea is that we know that a well-written assembly code certainly has the potential to be faster than the corresponding C++ code because it's a faster process to translate assembly to binary than it is to go from C++ all the way down to the binary level. And yet, with large-scale projects, trying to do the whole thing in assembly can certainly get difficult. Which is why, you know, when you think about large scale projects, you know, you're most likely going to still do a lot of it or try to do a lot of it in a high level language. But we might try to do still certain portions of it in assembly to boost performance, right? To try and optimize performance. And so we'll see a couple of different ways of incorporating the two together. The first is through what's creating an ASM or assembly block. Um, and you know, different compilers may have different ways of handling this, but in Visual Studio, we can create what's called an ASM block and start putting assembly statements in there. And there are some limitations, right? This is not, you know, exactly the same as just doing straight assembly as we've been doing. But a lot of the key things that we've been doing, we can also do within an assembly block as well, such as refer to the registers by name. If you know, your variables that you've defined at the C++ level, you can refer to those in the assembly block with your assembly instructions, right? Like, so with your move instructions and so forth. And most of the instructions that we've been talking about also can be used. So you can start out maybe doing some code in C++ and then break out and do some assembly code and then return to the C++ level and so on and so forth. But there are, again, going to be some differences and some restrictions, right, in terms of what's allowed or not allowed in the actual ASM block. And so we call this sometimes the ASM directive, right? But it's really two underscores and then ASM, short for assembly. And so that's that would be the starting point. And you can do things like maybe just, for example, have a single instruction within that block, or you could potentially have several instructions if you use the curly brackets. So that's the basic idea. Is the syntax here is underscore underscore ASM. Again, we can tag it to just an individual instruction, like what we did up here, or we can tag it in terms of a whole block, right, using the curly brackets. And then we can start putting multiple instructions within that block. Now, there are some restrictions. So the intention here, right, is that when you switch from your C++ code to temporarily doing some things in assembly, presumably, right, the whole idea is that what you're doing in your assembly block is going to have some connection to your overall C++ program. So, if we've defined at the C++ level, right, so this could be, within main, for example, and you started defining variables like, for example, int x equals 5, maybe int y equals 6, and make them uppercase to match what we did in the block. Then, so you can refer, right, to those variables, for example, by name inside the assembly block. And you'll notice in particular here, we're doing things like declaring these variables as type int, and then moving them into registers like EAX and EBX, because the size also matches there, right? Because we know that an integer is 32 bits or 4 bytes, which is also the size of a register like EAX and EBX. So as usual, you still want to think about those things, meaning that when you're working with your C++ variables, you want to take into account their size when you're using them with things like registers in your assembly block. But we can certainly refer to those variables by name, right? Meaning if there's variables you define, locally inside the body of the function, or if you have like parameters that you passed in your parameter list, you could also refer to those variables, right, by name inside your assembly block. And again, we can use most of the instructions as well, but there are some things that we've seen before that we can't do. And so in general, though, the intention is usually when you're doing this is that you're going to be working, right, with things that you've already established at the C++ level. So you've already created some variables and you're going to work and do something with those variables that you define at the C++ level in the assembly block. Because remember, this is just a block, right? After this block ends, we then go back to the C++ level, and then we can continue. And for example, when we get back to the C++ level, we could still work with X, right? We could still change X and do, a statement like X++, for example, or Y minus minus. So we can also, as we hinted at here, potentially have multiple of these blocks too. So we can, go back and forth as needed between the two levels. But examples of things that we're not going to be able to do are things like declaring, for example, trying to do dot data and then declaring assembly variables in the assembly block, or trying to define, an assembly procedure in the assembly block. Because the whole idea is that you're working with things that are coming right ultimately from the C++ level. And so because we might be doing a lot of things here directly in C++, like maybe user input, user output, and maybe a number of other things, but then there's going to be some specific things that we do in assembly, and then maybe we come back and we do some more, for example, at the C++ level. So we're not going to be doing things like, defining a procedure in the ASM block or trying to define variables in the data segment, but we can work right with variables that have already been defined. And we could even do things like, for example, call, one of the C++ procedures if we had another C++ procedure, which we'll see an example of that as well in the code example that we look at. But we can use instructions, a lot of the instructions like your move, add, sub, and so forth. We can use things also like the PTR operator, which we've seen that one come up in a couple of different ways throughout chapter 4. Things like length of and size of are not available, but we can use length and size instead. And then the type operator can be used both here and as we've seen in just straight assembly as well. So some things we're familiar with we can use, other things we're not going to be using. And then another case would be the offset operator. So that's another one that we can't use, but there is an alternative way to get the address of, for example, if you wanted to get maybe the address of X variable and maybe put that in ESI or something. There is an instruction called LEA, or load effective address, which does the same thing really as move, for example, move ESI offset X, and LEA ESI X, both do the same thing. So that gives us another way to still do that. So these are all examples of things that we can do. And again, we said that while the offset operator was not available, we can use what's called the LEA. And this can also be used in straight assembly as well, but the LEA, or load effective address, that's your alternative to the offset operator. And so we can still do a lot of things, right? In particular, logic that's going to be working with the C++ code, because that's usually the intention of doing this in the first place. And now registers are also available, certainly here. meaning things that we're familiar with, like the EAX, EBX, and also the lower level registers like AX, AL, ESI, and so forth. There is something that's important to take into account there, though, and that is how your ASM block is going to kind of fit into the overall picture of your C++ program. Because in particular, we know that when you write a high-level language code like C++ code, of course, the compiler ultimately is going to be what determines what the corresponding assembly language instructions are. And compilers are designed, right, to try and optimize things. And optimization, right, certainly involves registers, because we know from chapter 2 that accessing a register is certainly more efficient than accessing a variable from memory. So, meaning in general, right, when you're writing a high-level language program, behind the scenes, there's going to be register usage. And so one thing you have to also think about then is, well, if we start using registers in the ASM block, right? So there's some C++ program, C++ code, maybe that happens before the ASM block, right? And then after the ASM block, there's more C++ code. And are we going to be able to maintain things in the proper way as we go into the block and then out of the ASM block? In other words, are we going to be doing things in the ASM block that are going to mess up, right, the rest of the C++ program or not? And it depends really on which register we're talking about. So the X registers, meaning EAX, right, EBX, ECX, and EDX, and the corresponding lower levels, right, meaning AX, AL, BX, BL, BH, CH, CX, and so forth. Those are all designed to be safe to use within an ASM block. Meaning that, for example, what we're doing here, you'll notice, is we're saying stuff like move EAXX, move EBXY, and then add EAX EBX. And then down here, we hit the end of the assembly block. And again, we didn't write out a full lengthy C++ program, but you could imagine that in general, right, we may have a lot of things that happen before the ASM block that could certainly involve registers, right, like EAX. And we could also have a lot of things going on after the ASM block. In general, our C++ code certainly could be behind the scenes, right, using those registers for optimization purposes. And likewise, after the block, the same idea, right? We may continue to, at the C++ level, continue to use registers for optimization purposes. But then really what we would be concerned about is if something that happens in the ASM block is going to, for example, cause a major problem with the C++ code that comes after it. But the idea is that EAX, EBX, ECX, and EDX are designed in such a way that we don't make any assumptions about their values being preserved, right? So as we transition from the ASM block into the rest of the C++ program, the compiler, when it optimizes things, right, doesn't make any assumptions about EAX's value being preserved or EBX's value, or same thing for ECX or EDX. So in that sense, it means that it's not going to cause any problems, right? It's not going to cause any problems if we change the values of things like EAX or EBX in the ASM block, right? The rest of the C++ code is still going to be able to work correctly. But where we would get into problems is with things like ESI, EDI, which those are we know are our source and index registers, and EBP. And then, of course, we know from many of our discussions that usually you don't directly move or directly change ESP unless it's related to things like cleaning up the stack with the function call. But those registers, right, we do have to be careful about, because if we just, go in here and we set something into ESI, well, that's different, right? That's different than something like EAX, because ESI, it is assumed, right, that if we make any changes in this ASM block, right, when we get out of the ASM block, the code that comes after it is still reliant upon whatever ESI's original value may have been. So we might have had some C++ code, right, that may have ultimately used ESI in some way. And when we get back to the C++ level after the assembly block is finished, ESI still needs to have that same value. Right. Otherwise, that could certainly create major problems, right? If we just kind of, randomly change ESI to something else inside here, and then that's how we also leave the ASM block is with that new value in ESI instead of the original value. But what that just means is that if we are going to change it, then we need to just make sure that we restore it back to its original value before the end of the ASM block. As long as we do that, then we'll still be okay. So again, if we're going to change things like ESI, EDI, EBP, and even ESP for that matter, but again, we have to be very careful as we know about actually using ESP directly. But certainly if we're going to change any of those registers, then we need to restore them, right, before the ASM block ends, because otherwise that could certainly mess up the C++ code that comes after the ASM block. So again, it just means that you need to have some sort of way of restoring whatever the value of the register was before the ASM block started, either through another variable or even through the runtime stack, for example. But we just have to have some way of saving and restoring. So let's add a few more things here within our ASM block. So for example, just to kind of test the idea out, if we're going to maybe do a move instruction with ESI and EDI, maybe that LEA instruction, which would put the address, for example, of a C++ program into ESI or EDI, that's fine, because maybe we want to, do some work with that here in the assembly block, but we just got to make sure that we save and restore it, right? That's the only thing. So here we started out, and again, you can use the runtime stack for that. So that's, we talked about the stack throughout chapter 5. We talked about how it's used for function calls and how it does things like store the return address, but it can also be used as like a temporary storage, right? And we need to save and restore things. So here, what we did is we pushed ESI and then pushed EDI. And then if we want to do, for example, LEA, ESI X, for example, or LEA EDI Y, that's that LEA or load effective address. You know, that kind of thing is fine too. It's just we need to make sure that before we do that, we go ahead and save whatever the original values of ESI and EDI were, because they could have already been used by the C++ code that came before this block. And then whenever we're done using, so let's say maybe we move these in and then we have some code that maybe is going to actually do, you know, something with X and Y here in the ASM block. But when we're when we're done using it, we just need to make sure that we restore it, and we can restore it in this case with pop instructions, right? Because we pushed ESI first onto the stack, and then we pushed EDI on top of it. So now if we just do pop EDI first and then pop ESI second, well, now we're going to end the ASM block with those two registers still having their original values. So we're not going to have any problems when we then switch back to the C++ code after the ASM block ends. So just pop EDI, restore its original value, and then do the same thing for ESI, and then we're fine as long as we do that. So that's the distinction with the registers. If you're working off of things like ESI or EDI, or maybe even EBP, then you need to do something along these lines to make sure that you're not going to corrupt, right, the rest of your C++ program. But with the X registers like EAX and EBX, we don't really have to do that. So those registers are designed in such a way that we don't, the code that comes after this ASM block is not reliant upon whatever EX's value was before the ASM block started. So we don't make really any assumptions about those registers and their values being changed, right? Because in general, EAX is a register that changes a lot. But with registers, especially registers that store a lot of times addresses like ESI, EDI, right, ESP, EBP, we know that those four, ESP in particular, right, always stores an address, but the other three oftentimes also store an address as well. So, you know, especially when we're dealing with things that are acting as pointers, right, we need to be careful, and because those do need to be preserved. So we know that usually we don't use ESP directly unless there's, you know, something we need to do related to cleaning up the stack. But what we said here also would apply to ESP as well if you were for some reason, right, you know, going to try and use that. So you just want to think about those things. Think about how the ASM block kind of fits into the overall picture of what you're trying to do with the larger C++ program. And so there are those cases where we have to think about saving and restoring values, but not with the X registers. So here we don't have to worry about pushing and popping, for example, EX and EBX, right? We can just sort of freely use those registers and then just transition from here into the rest of the C++ program with no problem. So it's just those registers like ESI, EDI, EBP that are really the ones that we have to, you know, worry about in terms of restoring the values. And this LEA is that load effective address. So that was our alternative to the offset operator as far as if we need to get the address of something, in this case, the address of one of our C++ variables that we're going to be working with inside of this ASM block. So here we talked about things that we can do. Okay, so that's the basic idea with embedded assembly. So it's really convenient, especially if you're doing a lot of things in C++, but you just kind of want to break out, maybe do a few specific things in assembly, and then return back to the C++ level. So we'll look at an example. There'll be a little bit more going on than what we did here, but we looked at a lot of the basics here. But we'll look at an example where there's going to be a couple of ASM blocks, and we'll have some instructions in those ASM blocks. We'll also have a point where we look at a function call that happens in the ASM block. So that is another thing that we can do, is things like function call, meaning in this case, we've talked about procedure calls, right, when we were in chapter 5, but we can also do things like in the ASM block, for example, call one of the functions at the C++ level. And so we'll look at how that's going to work out as well. And so what we'll see is before that function call happens, because the function actually has parameters, right? And so there's going to be a couple of things that we push onto the stack before the function call takes place, meaning before the actual call instruction. And then there's going to be a little bit of cleanup that we do when we return back. So again, a little bit different than the way we handled some of these things when everything was just straight assembly. Because one thing that you do have to think about is when you think about the connection between your C++ function and things like the parameter list, and how that's going to match up with the corresponding function call. Well, we know that if we write out a function call in C++, right, we just in our parameter list in our parentheses. Usually, right, it works out to where the number of arguments in the parameter list matches the number of arguments in the function header, right? Unless maybe we're doing things like default arguments, but otherwise, that's going to match. But at the assembly level, right, we also can keep in mind that those parameter variables are really coming from the stack, right? Those local type variables. And so we can do the same thing directly in assembly. It's just we have to think about what kinds of things are going to be pushed onto the stack before the function call itself takes place. So the function call itself, we know, is going to push the return address, because we learned that's what the call instruction does. So in this case, we're writing out the call instruction in assembly, but then what we're calling is a function that's written out right in C++. So we have to kind of think about something a little bit differently here. And there are going to be a couple of parameters in this function, because the function itself is just going to do a cout statement to display the output. And the idea is that what we're going to do is we're going to push 2 arguments onto the stack first, and those correspond to
the parameter variables, right? Meaning the variables that we defined in the parentheses for the parameter list of the function. And so those are going to be pushed first, and then we're going to push the return address when we hit the call instruction. And then we have to also think about the issue of cleanup. Because in our examples, what we were doing back in chapter 5 is basically whenever we had a input to a function, it was a register, right? We would, for example, set up some registers beforehand and then, use those. But here, we're actually wanting to call a C++ procedure and use those variables directly, right, from the C++ procedure in the body of the function. So we have to form that connection between the call, which is in assembly, right, and then the actual function, which itself is written entirely in C++. So in this case, the parameters are not registers, right, but are variables that are in that parameter list. But the connection comes down to the runtime stack. So before the call instruction, we're going to have a couple of push instructions, pushing those arguments onto the stack, and then we're going to use those at the C++ level when we call the function.
And so we'll see how that's going to work out. But the other aspect of it is also the issue of cleaning up the stack, right? And this also is a little bit different because we know that at the assembly level, what we did is at the end of the procedure, right, you would hit that return instruction. And at that point, the only thing that we were really thinking about was, well, we know that when you hit that RET or return instruction, it was going to pop the top thing off the stack, and it was going to take that address, right, and then place it back in the EIP, because that's how you would get back. Now, in this case, we'll look at a void function, so there's not a return value, but nonetheless, when we hit the end of the procedure or function, it's going to still do that, right? It's still going to take that address, pop it off, place it in the EIP, and that's going to take us back. But when we get back to main, for example, we're still going to have those two things, the two arguments that we push, those are still going to be on the stack. So it's going to really be up to main to clean up the rest of the stack when it returns back. So we call the test function when the function ends, meaning when we hit in the C++ side, meaning when we really hit the right curly bracket, it's going to pop right that top element off the stack and place it in an EIP, and then we're going to go back. But then we still have some more cleanup work that we have to do with the stack when we actually get back to main. Because at the C++ level, if there's any sort of cleanup work that needs to be done, then it's really that's on the calling function to do that cleanup work, as opposed to the called function. So what you're going to see is that after the call instruction, there's some cleanup that we do with the runtime stack, really. And there's a couple of different ways that you could potentially do that, but we'll see that what it really comes down to is adding the right amount to ESP. Because we know, going back to all our discussions from chapter 5, that because the runtime stack grows downward from higher addresses to lower addresses, whenever you pushed something, you were going to subtract, right, the value in ESP. For example, if you pushed a D word, then you would subtract 4, or if you pushed a word, then you would subtract 2. And likewise, when you're wanting to pop, right, something off the stack, then you would add an amount to ESP, such as adding 4 if you're wanting to pop a D word, right? Or adding 2, for example, if you're wanting to pop a word. So really, when that procedure ends, we just have to update ESP. So there's a couple of different ways you could do that. I mean, you could do, for example, multiple pop instructions, but we'll actually see a way of doing it with the add instruction with ESP directly.
because we know the runtime stack really just comes down to that question of what is ESP pointing at. But there will be a little bit of cleanup work that we do after the call instruction. But that's one thing that we'll see as well in that example. So a couple of ASM blocks, and then we'll eventually get to a point where there's going to be a function call in one of those ASM blocks.